This lecture is about exploiting format strings. Now, format strings might be pretty foreign to some people not used to C, but for C programmers, they are very useful, allowing you to easily print stuff to the console without having to worry about how to format it and creating buffers in between and so on. So for C programmers, this is important because memory management in C is difficult and time consuming. So printing something straight to the console while formatting it with data for C is very nice. However, it also introduces the potential for vulnerabilities. So we're talking here about formatting functions like printf and related functions. So what they do is they take a format string and they take some format parameters. So printf is a bit of a special function in the sense that it can take an arbitrary number of parameters. Now what the function does is it takes the format string and interprets the % sign as a format. And this format will result in a formatted number, string or whatever based on the template specified after the %s. The value filled in is taken from the extra parameters that printf takes. So, for example, if the format string has %x, it's going to convert the next format parameter to a hexadecimal string and add it to the output. Now again, this is very useful for a C programmer so that they don't have to think about how much space would this take, where do I store it, and so on. Now, this is nice. However, if you're careless, you might not remember about the format string, and you might allow the end user to specify the format string. Now, what could happen? What happens if the format parameters are not actually there? So we call the printf function with just this one parameter, the format string specified by the user, and without the actual parameters used to fill out the formats. Now, take a moment to think about what you expect would happen in this case. It turns out that parameter passing for printf works exactly the same way as for other functions that do not have an arbitrary but rather a fixed number of parameters. But in this case, simply the user can specify as many of these parameters as they want. So first we use the registers and then we use the stack for the remainder. Now what would happen if some of these arguments were missing? Now, just as before, there's no special handling for this. The function has no idea how many parameters were actually specified. So it must assume that they are simply on the location where they would have been if they had been passed correctly. That means that they are filled in with whatever happens to be on the spot where they were expected to be. So either in the register they were expected to be or the stack location. Now this means it's basically going to take random data and use it as a substitute for the actual data that should have been filled in. So this means there's a great opportunity for information leaks. We can grab data from pretty much all of the stack because the $sign specification allows you to specify the parameter position. It's very easy to just leak any data from the stack. Well, this is useful of course, but can we do more? It turns out the attacker can indeed do more. There's a little used format specification, %n, that has a very special purpose compared to the others. It does not actually generate any output. Instead, it stores the current length of the string, allowing you to figure out how long parts of the string actually are. Or, if you're using something like sprintf, how much space you need for a particular part of the string. So, in some obscure cases, this could be useful. However, it's far more useful to attackers. So what happens if you encounter %n? Well, %n also takes a formatting parameter, but in this case the parameter is interpreted as a pointer, and the pointer is the location where the length is to be written. So it stores the number of output characters so far, and it stores them to the pointer passed as a parameter. Well, this means if you control the format string, you can do an arbitrary write. Because you can write the length, which you control because you control the format string. And you can write it to whatever location you can point the parameter to, which is pretty much anything on the entire stack. Here we have an example of a vulnerable program that has a format string vulnerability. So in this case, the vulnerability is in the call to the snprintf function. So what does snprintf do? Well, it formats a string and then writes the result to another string. And the n indicates that the length of the string is specified. So in this case, the target is buff, which is 256 bytes, and we also tell snprintf this. So this avoids a buffer overflow, which is nice. Well now, and this is a sensible mistake to make, if you're just intending to write the string there, you might forget that the other parameter is actually a format string, and you simply pass the string that you would have wanted to write there. In this case, this string is attacker controlled because it's a parameter specified to the program. So, what does this function actually do in this case? It's going to format argv1, which means that whenever there's a person sign, it's going to be interpreted with a special meaning, getting a parameter from the parameter list and then formatting that into the output. The parameter list is not specified here. So there is an arbitrary number of possible parameters, but they come after the format. In this case, 0 additional parameters are actually specified, which means that whatever formats we're going to put there are going to be taken from other locations where there is no information about any parameters. So it will be interesting to take a look what kind of output we get there. Additionally, we have some printfs that will help us debug any issues we might encounter. So we write the length of the buffer as well as the contents, and we also have a variable y. Now we print for the variable y its value as well as its location. So guess what? Our goal is going to be to change the y, corrupting data. Now let's experiment with the program that we just saw. So compile the program, disabling of course all the protections again, and now let's just call it with the format string. So in this case the format string is %lx. So the person sign starts the format, the L indicates the size, which is a long, so the default is an integer, and the X means format this number as a hexadecimal number. So this is exactly what happens. We see that the buffer is printed, and we see that the hexadecimal value is indeed printed here. Now this is just whatever happens to be in the location where the first format parameter should have been. Well, y is of course unchanged, but we're not concerned with that yet. So let's see what happens if we add some more parameters. We now added a whole bunch of %L parameters to get a good idea of what is in the registers and what is on the stack that we might be able to use. Right, so we see a bunch of values printed. These all look like pointers, right? So the first one, the code pointer, and the others might be heap pointers, or library functions, or perhaps stack pointers. So let's take a very good look at the numbers that we see after this. Is there anything that stands out? Take a good look. So if you haven't found it yet, consider whether there might be something with ASCII, and consider that the numbers are little endian, which means that from your perspective, they're probably the wrong way around. Found anything yet? Consulted the ASCII table perhaps? Well, if you had, you would have found out that this number right here actually corresponds to the first number you see here. So 0x34 is actually in the ASCII value for the character 4. 30 is the ASCII character 0, and there's another one. So these two match. So why is this relevant? It means that we can actually write to these parameters, which is very interesting if we're going to do a %n attack. So we see that the numbers we write at the start, so by generating the output, are actually visible as parameters because the parameters essentially cover the stack. Now, let's take a moment to think how we can use this. Well, first, let's verify. Is it indeed true that whatever we put there is going to end up in this parameter? So this format string uses the positional indicator, the $sign, to grab exactly the 8th parameter. And now we start the string with the letter A to make sure that we have something that's easy to recognize. And indeed, we do get this output. The person Alex is indeed sending us all the A's. So it means that whatever is in the format string ends up, as a result of the format string, I should say, is also visible as a parameter through the stack. This is very interesting. So let's try this instead. What do we see? Something changed. Y is now actually 8. It was 1 before, and there's nothing in the program that actually writes to the Y. So we managed to achieve something. Now, what did we do? First of all the A's are of course not very useful. Instead, what we did is replace them with a pointer. And the pointer must of course be specified little endian. So we had the pointer to Y, and we're specifying it here as a little endian number. Now, there's also an issue. The pointer is 8 bytes. However, there are only 6 non-zero bytes. Obviously, we cannot put any 0 bytes here, because this would terminate the string. Instead, what we do is, if we look back at the previous slide, we see that there's a parameter that's actually 0. And this happens to be number 6. So let's reuse this. Let's reuse parameter 6 to generate a null byte. We use this format, which generates a character, hence the C, and its input is format parameter number 6. So this just generates a null byte for us. Now the output starts with a pointer to Y, and at that point we use this format. %8$n. We're using format number 8, which we saw was the format actually at the very start of the string on the location on the stack, and use the %n format. So we're going to write the current length to the Y, which we can see is exactly what happens. So very nice. We're now able to write the length of the current string to a location that we can pick. That is great. However, let's say we want to write the address of a shellcode, which might be something like this. That's a huge number, right? So this is way too large. It's actually almost 2 to the power 47. Way too large to go through. Even if we don't really need to store everything, just looping to this number takes quite some time. So we don't really want to make an output string that is this long. So what can we do instead? Well, the shellcode address is too large to be realistic, but we could write it in chunks. So let's say we first write the lowest order byte by setting the length to a length that is basically the value that we want, modulo 256, which is the number of values that can be stored in a byte. Or we could do it with a short, with 2 bytes. Now what do? We first write the lowest order byte, or lowest order 2 bytes, by having the length modulo 2 to the power n be equal to the number that we want to write. And then we separately write the other parts of the output. By doing this, we can use multiple steps, and we don't need to have such a large number as a length. We have now seen some idea of how to use the format string vulnerability to create an arbitrary write, and we've seen an example of how to exploit it. However, it's still not easy to get to the return address, right? So in stack buffer overflows, the return address is at a fixed offset and is very easy to reach. In this case, we have to specify a pointer to it, and in a changing environment, that might not be easy at all. Are there easier ways to exploit an arbitrary write? Yes, there are. So we want to write to an absolute address and still be able to hijack control. So an alternative would be the global offset table. Now this is used to lazily load library functions. So any program uses a bunch of library functions, at the very least those in the standard C library. Now these ones, at least traditionally, were looked up lazily. So the first time you call a function, say printf, it's going to take a look in the library file where printf actually is, and then fill in this number in the table that is called the global offset table, or GOT. On the first call it's stored, and because it's in a fixed location, it then reuses this value every time. Well, the GOT is fixed in memory, so it means that we can easily find a location where there's a code pointer. And whenever the function is called, so say the printf function, this code pointer is called. So we can use this to reach our shellcode instead of the return address. And now we have an address that's stored in a fixed location. So how do we find where to write our address to? Well, it's easy to figure out the layout of the global offset table. First of all, the program has stubs in the PLT, which is a program linkage table. The PLT contains entries that allow us to easily call these functions like printf, and if it's the first time, look up the location in the process. Because the global offset table has essentially a value that will load the correct function into there. And then the next time we can call it directly. So here we see clearly it's jumping to a pointer that was read from this address, which is the address that we need to corrupt if we want to replace printf with our shellcode. Likewise, we can use the readelf utility, and readelf will also find this entry and the same address. So this means if we are able to use printf to override this address, then whenever we call printf, the program will jump to this function, for example our shellcode. So this is a rather convenient way to exploit arbitrary writes into getting control flow hijacking.